morning, everyone, and welcome back to day 5 of the short term training program on quantum technology, applications, and implications conducted by the Department of Physics, Assam University, Silchar, in celebration of the International Year of Quantum Technology. We are delighted to have you with us for another exciting day filled with inspiring lectures from leading experts across diverse fields of quantum science and technology. My name is Devika Dakkar, and I will be your anchor for today's session. To begin today's program, it is our privilege to welcome again Professor Aditi Sende, who will be continuing her insightful lecture on quantum communication networks. Professor Aditi Sende is one of the foremost researchers in quantum information science. She is a faculty member at the Harish Chandra Research Institute, Allahabad, and has made seminal contributions in quantum entanglement, quantum cryptography, and quantum networks. Her work continues to shape the theoretical landscape of quantum information and is vital in guiding emerging experimental platforms. Ma'am, it is our privilege to have you with us once again. Let us all rejoin in welcoming her for this session. Ma'am, you may take your time.
Thank you. Thank you very much. So, can you see my screen?
Yes, ma'am.
Okay. Okay. Thank you for listening for last two of my talks, and today is the last one. So, I continue quantum communication and actually quantum communication networks. Uh, as probably some of you have listened, that first two lectures were communication without security that I have talked about. Uh, uh, in particular, in the first lecture, I have talked about how to transfer classical information by using quantum state. And we have shown that if you use quantum mechanical properties, quantum states, composite systems, then in particular entangled states, then actually you can double the capacity. And this was in the first lecture where I was talking about quantum dense coding network, etc. Now, in the lecture two, the last day, yesterday, I talked about how to transfer quantum states among various nodes. So, in particular, how to also, I have also talked about recent papers, recent words, how to spread entanglement over different nodes. And this is the building up of quantum internet or quantum communication networks, and this is one of the important current research directions in this field. And this is probably, there are several open questions. I have shown that some problems can be solved. There are a lot of works going on theoretically and experimentally. Many things are very hard to hard to address even, because this is mathematically quite involved in this when we talk about quantum internet. Similarly, it's very challenging for experimentalists to build quantum network. So, but there are many proposals in this community, as well as there are a lot of experiments going on around the world, also in India, where the people try to kind of build quantum communication network. So this is one of the primary area, or one of the thrust area in this field of quantum devices, how to build quantum communication devices in network. Now, today actually it's a bit different topic that I will be talking about, but quite interesting and extremely important from national security and also for our personal life. So this is a secure quantum communication. It's in other words quantum cryptography. Now, classical cryptography is a very well established subject, very developed, and still there are a lot of work going on. And on top of that, we today we will be talking that how the classical cryptography, or what are the extra thing you can gain, or I mean in terms of security, by using quantum mechanics. Now, I feel that this lecture is extremely important in communication, or in for national security, as well as in for our life, as because somehow, probably now you know that whenever we on our or we want to call someone in mobile, then there are some messages coming that you are don't disclose your bank account number, don't disclose your personal information, so that the people can actually take out the money. So there are a lot of frauds, internet or cyber frauds are going on. So particularly this time, when this is, I mean, last few months, we have seen that many of us have actually got cheated by certain calls or certain video calls and so on. So there are national, level kind of cyber security branches in India. They from government. They are now kind of telling, or kind of announcing how to make your money or your things secure from these frauds. And so these are all in this. This is the area which today I will be talking about, and I will show you that how quantum system can help us to get higher security, or rather the security in general. So this is the goal, and so I today talk about secure communication, which is quite different than the communication protocol that I had discussed in last two lectures. So, as I was telling, that in communication there should be at least two parties, and sender and receiver. And sender, I call it Alice, and receiver, I call it Bob. Here also we have the same, but there will be a third party, and that's the important one. So that third party is the eavesdropper or the fraud. Okay, so sender wants to send certain information to Bob in such a way. So here, as I have kind of in my first lecture, I have said that there are any communication protocol, there should be few steps. One is encoding, then there will be sending, and third one is a decoding. Now, in this secure communication protocol, it's extremely important that Alice encodes information in such a way that third party cannot gather any information that Alice is sending to Bob. So you know that when we, for example, in our daily life, we use cryptography heavily. So, for example, we when we log into the bank, so you can think that I am the Alice and the bank is the Bob or the receiver. So Alice has to encode, or say, for example, set the password in such a way that third party cannot actually break the password. And so whenever we actually set the password, we know that there are some kind of messages coming, like use capital letter, use special symbol, use numbers, and so on. And it should be 9 digit, or 9 or 10 letters, and so on. So these kind of information actually is required to secure your banking information from the third party, or the fraud, or the eavesdropper. So the idea is that you one kind of so the information Alice has to encode in such a way that Alice can send only to Bob, not to the third party. So this, we every day we do that when we use internet banking, when we use the say internet you use for shopping in some shopping website, and so on. At the same time, this is also related to the national security, that we can understand when there are war going on, then the messages should be sent from one battalion to another one in such a way that in the middle party should not get the information that is sent to the two parts of the, say, the soldiers. and so on. So the, as you can see, that the communication or the cryptography is extremely important, or one of the important area which is kind of developed over the years. And because this is important from national security to our personal level security, or the in current world, for example, this online banking, etc. So, classical cryptography, as I have said already, is a very well advanced subject, and we are using this cryptography for a long time. So, this is kind of a historic slide, as we see that the Skytel is one of the oldest one from Greek. There are Indian one which is also a cryptography which called Katapayadi Sankhya, and this is also the Indian. And there are several countries have their own cryptographic system, and probably the recent one by Enigma, by German, which was used, probably many of you know that this was used during World War II. So these cryptographic schemes are useful. People understood that for a long time, and so the several countries developed this kind of different cryptographic scheme. So today, first I will talk about one of the oldest cryptographic scheme, which is known as substitution cipher. Actually, it was done by Julius Caesar. So it's also called, for example, I mean, one of the substitution cipher is known as Caesar cipher, and this is a simple way to hide information from the third party. Now, this I have also discussed in the first talk, but just to repeat, suppose I want to send that currently I am in Pune. So instead of sending Pune, Alice sends SXQH. Now you can guess that P is QRS. So three places forward in our alphabets to encode the message. So U is X, so U is VWX, N is again three places forward, and E is FGH. Okay. So as you can see that here Alice has shift three places forward. So instead of sending Pune, Alice will send now this SXQH to Bob. Now, Bob has to decode this message just by reversing. That means three places backward, and immediately Bob can gather the information that Alice is currently in Pune. So, this is the kind of very easy way, and this is exactly called substitution cipher, because instead of P, I substitute that with S. I can make it more complicated, like the first letter with for three place forward, second with five, and the third letter with seven, E, the fourth letter with nine, so that it is kind of you know it follows some kind of odd shifting and so on. So you can make it more complicated, but the idea or the goal is to encode the information or the letters to certain other letters, and so substitute it to the other letter or to some other things like another symbols and so on, which are used in your in the community, and then you send that substituted text to Bob, and so that Bob can decode this message, but it cannot be decoded by, or it cannot be the information cannot be gathered by eavesdropper. However, these ciphertexts have some structure, and so there is something called frequency analysis, and so by which you can break this easily. So the eavesdropper or the fraud, always in this talk we will discuss that the fraud of the eavesdropper is very powerful. So they can actually decode the message. I mean, they can do anything. So this is the one thing, because always you have to assume that the enemy is most powerful. Assuming that enemy is weaker than you, always make your system weaker. And so in this entire discussions, we will always discuss that enemy or the fraud is always powerful, the user is very powerful. So what do I mean by structure? So any language has some structure, because for example, I have used again the English letter alphabets to encode the message this morning. uh, so I have just shift three place forward in the alphabet to encode the message, and similarly Bob can decode. So this has there is some letter, there is some frequency analysis which can be done. For example, if you I mean, you can search easily that relative frequency as the first letter of an English word in a text is in this fashion. So typically T comes in our anything what we want to convey the text. T comes 16%. On the other hand, A letter comes 11.7%, O comes 7.6%, and so on. So as you see that if a person this way, if you encode, and if someone finds that some letters are coming more frequently, immediately he or she can guess the original plain text contain that letter already. So suppose you get more time x, then as it is in the in this from this table, and you are guessing the first letter, and so you understand that u correspond to t, and so on. So this is the way, and this is not only for the English, but you can find in your own language that some letters are coming more often. So I am Bengali. I think the in case of Bengali, it's a ko is coming more often, and in Hindi there are something which you can also find. So there are several. So these are known. These people have known because there are crypto analysts actually knows how to break these kind of substitution cipher by using frequency analysis. And this is one of the very interesting subject, and if you're interested, I am talking about letter frequency. One can have word frequency. For example, in English language, we know we use the very often, and so this can be easily guessed, and after that, slowly you can guess some of the words, and in this way you can actually I can get the entire information that Alice is sending. So this is not the way one can send information properly. But there are something called one-time pad in classical cryptography, which can be shown to be completely secure. So what is one-time pad? Suppose Alice has the plain text which Alice has encoded in the bit strings of zeros and one. So here I have done. So this corresponds to say some letter or some word or some message. And now Alice also has some key. Now this key is a random sequence of zeros and one. And this random is extremely important. What now Alice will do? Alice create a cipher text, which is actually the plain text plus key modulo 2. So you see, 0 0 modulo 2 is 0, 1 0 modulo 2 is 1, 0 1 modulo 2 is 1, 1 1 modulo 2 is 0, and so on. So here you add these two modulo 2, and Alice, instead of sending this plain text, Alice creates a cipher text to which Alice is sending to Bob. So now the cipher text is sent to Bob through public channel, like in say by using newspaper or by using phone call, is by using SMS or anything. Now the important point is that the Bob has the same key as Alice. So this is the, as you see, this is same as Alice. Now what Bob can gather the information how? Because the cipher text plus key modulo 2 will give me the plain text, and you can easily do that 0 0 0, 1 0 is 1, 1 1 is 0, and so on. So this plain text and this plain text is same. So you have a plain text which has some bit strings, zeros and ones. You always, whatever language you are writing, you translate that to an bit strings of zeros and one. Alice and Bob has identical key, and the key is a random sequence of zeros and one. Now, Alice can just do the plain text plus key modulo 2 and send, this is called ciphertext, send to Bob. Now, since Bob has this identical key as Alice, Bob will do that. Bob, after receiving the ciphertext, Bob actually makes the same thing, that ciphertext plus key modulo 2, and Bob recovers the message plain text. This is extremely secure, and I mean it's just secure. Okay, so it is completely secure, and one eavesdropper cannot get any message if Alice and Bob has the identical key, and if they want to send in this way their text. But there must be some method by which Alice and Bob share a secret key. So, as I said, this is extremely important that Alice and Bob share an identical key, and then only it will work. But how will they share the identical key? Whether they meet in some place, whether, because in cryptography, as I said, except Alice and Bob, others have been thought of as enemy, or the fraud, or the third party, or the eavesdropper. So you cannot send the key, that you can suppose you create the key, Alice can create the key in her lab and then send by courier, or send it via with I mean send it to with the help of another person, another friend, to Bob, or in national security another soldier to Bob. You never know. So whoever is the recipient and the sender should only communicate and can have identical key. No third party can have identical key. So this is extremely important, that they should devise a method by which Alice and Bob can share an identical key, and this secret key is a random binary sequence at Alice, and the same as Bob, and importantly, no one else has it. So this is very important. Hello, hello.
Yes, ma'am.
Yeah, yeah. You can see my screen, right?
Yes, ma'am.
Okay, thank you. Okay, so this is the very important point, that the sequence, the key that Alice and Bob has, they are identical. They should devise a method by which Alice and Bob can share this secret key. So this is the second point. And the third is the key that they generate is random binary sequence of zeros and one, and these 3 points are not very easy to meet. And another two important point is that one should not use the key twice. So even if you suppose the plain text is changing every day, right? Because suppose I want to send some message every day to another portions of the soldier, then every day the message is changing. So you cannot use the same key to twice to send the message to the another part of the another team of the soldiers. You have to have a different keys. So this is very important, and this was a mistake that I think Germans did during Second World War. Now, another important point is Q should be as long as the plain text, and that is also extremely important, because once the if it is shorter, then you have to use twice, and this is dangerous. And so you one should not use the key twice, and one should not, and the key should be as long as the plain text. Now, Alice and Bob can generate secret key if they meet before they actually send the encoded message. This is, of course, possible. But can they generate secret keys without meeting? And this is extremely important. And so, a classical case, security depends on whether a mathematical problem can be solved or not. And there are two problems which typically used and probably you have heard of. One is discrete log problem, another is prime factorization problem. Now, today I am going to discuss only the prime factorization problem. So, the goal is to find the prime factors of an integer, and the integer is known, but the prime factors are not known. So, here there are two-digit number 57, and so we can easily find what are the prime factors 19 and 3. Now, here the prime factors, which are the, I mean, integers prime factors, here I am assuming in this entire thing that none of the prime factors is known. Okay, so I will give you an integer and you have to find the prime factors of it. Now I type this huge number. This is a 118 digit number, and you see that to find the prime factors it's not easy. So it is not at all easy to prime factors of this number. And as you see, its last digit is odd, and so it's 2 is not surely the factor. And so it's not at all easy, and not only it is not easy for me or for you, it is known that it is not easy for anyone. So, for example, instead of this 118, let's make bit life simpler. So, I have used 35 digit, and then you can find that if you have a there is a prime factorization algorithm known, existing algorithm which we can run in a classical computer like our own computer, or in a very good computer like a big substation and so on. Then this will take around this many steps, and it will take to solve this problem will take 130 seconds. However, if I go on increasing the number of digits, then it will take a huge time to solve this problem. And mathematically speaking, to factor an n digit number, known algorithm, existing algorithm that you can run in the best computer in the world may take huge time. And this huge time means that with the increase of number of digit, the time taken will be increasing exponentially. So, so that means if I make it 35 to 50 or so on, so once I increase the number of digits, the time that we by which we can solve this problem actually grows exponentially, and that means it will take a long time, actually huge time. And so this problem, and here I should two points to be emphasized. One is this is the algorithm, the existing one, which can take this many steps to solve an n-digit number, n-digit integer. On the and the second point is uh, the existing algorithm takes this time is not doesn't depend on the whether my hardware is very high end or so on. So it's actually it's this is with a very good computer. That means it's best computer in the world will take this much of time. So there is no efficient classical algorithm exists till date to solve this problem, that to find integer prime factors of an integer. On the other hand, Peter W. Shor, American mathematician, he solved this problem. He showed that if you use quantum mechanical principle, in particular superposition, then that can solve this problem efficiently. And what do I mean again efficiently? As you see that here with the number of digit, the time taken grows exponentially. Here it is polynomial. And this is Peter W. Shor, and this is one of the breakthrough results in quantum technology side and technology field, and probably this is one of the important results which motivate people to build quantum computer, because this is really a breakthrough which shows an exponential speed up by using quantum computer. And just to tell you that what is I mean according to in the what I said looks like that. So in case of classical computer, this grows. So x-axis is number of digit d, y-axis is number of operations. So once I increase the number of digit, then this increases exponentially. So this is best classical algorithm known as number field sieve actually take exponential constant into d to the power one third. So in other words, it's exponentially growing curve. So once you increase digit, uh, it will increase heavily. On the other hand, if you use Peter Shor's algorithm, then it increases polynomially. So it's a constant into d cube. So it's a cubic polynomial you can think of. And so this is the thing. So clearly, quantum computer beats the classical algorithm, and not only beats, you get an exponential speed up if we are able to build a quantum computer. Now, apart from this, there are several algorithms around that time were discovered, which were shown to give a higher efficiency than the classically known algorithm. One is Grover's algorithm, which is a quantum search algorithm. Here, that requires a classical existing algorithm requires n steps, while quantum computer will take square root of n step and so on. In Deutsch's algorithm, actually classical computer take some n steps, and here quantum will take a single step. So in all these algorithms discovered over the time, and all of them shown that it classical computer can or quantum computer can be more efficient than the classical one, and you can actually get a higher speed up to solve certain mathematical problem. So this is really a revolution in quantum technology, and just like building a good candle doesn't lead to LED bulb, so making a very good classical computer doesn't lead to a quantum computer. So this one should also kind of emphasize at this point, because classical computer is built on the principle of classical mechanics, electrodynamics, and electronics, and there are some quantum effects are there, but they haven't used properly. You don't explore all the quantum properties that you require. And so, for example, when you use laser, etc., that also build up on quantum mechanical principles, but you don't explore all the properties of quantum mechanics. On the other hand, quantum computer really explore all the quantum devices that we discuss in probably in all you have learned in this or you have heard in this workshop. All of them somehow are giving you a higher speed up, higher precision, higher efficiency, because we explore or exploit all the quantum mechanical principles. Now, there are quantum supremacy was already kind of reported. So Google, for example, claims in 2019 that they have quantum computer which are actually 53 qubits that can finish a task in 3 minutes 20 seconds, while classical supercomputer to solve that problem requires 10,000 years. So this is actually really a exponential speed up they reported, although their claim was later on kind of turned down, because IBM and also the researcher from China showed that no, this problem that they have addressed can be solved by a classical computer by 2.5 days. But indeed, by using quantum computer, you can solve that problem in 3 minutes 20 seconds. So you don't get an exponential speed up, but of course you can get higher efficiency. Recently also in 2024, and it's in November actually, last year they also have Google again reported some computer which are where they have did some error correction protocol, which are extremely important to build quantum computer. And so that's a very important breakthrough results in recent time, where we are heading towards quantum computer with error correction, which are known as fault tolerant quantum computer. I'm not going into detail. Now, just to remind ourselves that in classical computer, the basic units are bit, which is among zeros and one. On the other hand, in quantum computer, the basic unit will be qubit, as we discussed several times in last two lectures of mine. that quantum bit is an arbitrary two-dimensional quantum state written as alpha 0 plus beta 1, where 0 is one of the one states is psi and 1 is the orthogonal state of psi. So this is psi part, and alpha beta are complex numbers, and there is due to normalization there will be mod alpha square plus mod beta square equal to 1. And to build a quantum computer, just like classical computer, in a classical circuit, we have some universal gates, which we learn in our college on school, that there are classical gates which are universal, or and or and not, or NAND gate. Similarly, in it is also known that there are some universal quantum gates required to build quantum computer. So I have there are four actually, but I have here listed two of them. One are Hadamard gate, as you see that it goes from the 0 to 0 plus 1. So this is kind of superposition principle is explored here, and this is extremely important gates which we require to generate or to get advantage of quantumness in a circuit. And there are also another gate which is C naught gate, where you actually apply it on 2 qubit gate, and this is also extremely important because these gates are used to generate entangled state. And as we have shown in last two of my talks, and today also I will show that entangled states are important in communication devices, and probably you have also heard that it is extremely important in quantum sensors, quantum computer, it's in other quantum devices and so on. So to build quantum devices, we really require entangled state or the superposition states. And so quantum computer is these two gates are extremely important to really use properly the quantumness in the circuit, so that we can get the advantage in speed up. So the quantum circuit, just like a classical one, will be built by using all these quantum gates. And so you can think that there will be some input state, and by using this, and the circuit will be, we then there will be input where you put it in a circuit where you use, say, for example, Hadamard gate. These are the control gate and so on, and can build this kind of states which actually can be shown to be an entangled state. And so this is the circuit to build an entangled state. And this can be and in this way you can make a bigger circuit to execute any quantum algorithm that I have talked about, like Shor's algorithm, Grover's algorithm, and so on. So again, come back to the problem. So as I have shown that classical cryptography is based on certain quantum. The security of classical cryptography is based on the belief that some mathematical problems cannot be solved in a classical computer. And two of them that people use to build classical cryptography or crypto systems in current time is the discrete log and prime factorization problem. And as I have said, that these mathematical problems can be solved using quantum mechanics or quantum computers. That means the entire story, as a twist, as I said, that quantum mechanics makes all current crypto system insecure. So whatever using the internet banking, national security, or our online shopping, everything actually is based on certain things, like some mathematical problems cannot be solved in polynomial time in a classical computers. Now if we can build quantum computer, these problems can be solved using quantum computers, and hence the crypto systems based on these mathematical problems can be solved. And so these crypto system, all current crypto system, become insecure. So that actually questions that how can we generate secret keys without meeting? Can quantum mechanics help to generate keys without meeting? And this leads to the quantum key distribution that I'm going to discuss. Now, natural question that is it secure? The answer is yes. And not only yes, this QKD that I will be discussing is quantum key distribution remains secure even when quantum computer is acting. So even when you eavesdropper can use quantum computer, which is more powerful than the classical one, as I was trying to argue you. And so if eavesdropper has a quantum computer by which he or she can solve certain mathematical problem in polynomial time, even then the quantum key distribution or quantum cryptography that we will be discussing, will remain secure. And so this is one of the important area, as you can understand, from national security to our personal life. So, what is quantum key distribution? The two known protocols, which are there are several key distribution protocols over the time, but the first two was proposed, one by Bennett and Brassard in 1984. Another one is by Arthur Eckert, 1991. So this is actually Bennett. So this photo I have taken when Charles Bennett was visiting us at Harish Chandra Research Institute. This is Brassard and Arthur Eckert. So three of them are discussing in a conference, and this is the photo. And so first Bennett Brassard proposed this 1994 protocol, and then the Eckert. So I will discuss all of them. And so Bennett Brassard proposed this protocol in 1984. Eckert was in 1991. So again, the BB84 protocol involves two parties, Alice and Bob. Now the protocol runs as well in this as following. She prepares randomly one of the states. So this is the plus z, minus z. This is the eigenvectors of Pauli operator sigma z, and this is the eigenvector of the Pauli operator sigma x. So she prepares randomly one of the four states and encodes the information in this way. If plus z or plus x, then the bit is 0, and if minus z and minus x, then the bit is 1. Then she sends one of the state she prepared to Bob. And now Bob measures randomly by choosing the basis Z and X. Now it's a single particle system, and so we know that there are Stern-Gerlach experiment which can actually perform the measurement. So you actually put the Stern-Gerlach either in the Z basis, sigma Z basis eigenvector, or in the sigma X basis. This is the basic experiment that we all have learned during our MSc physics course, and this is the first experiment described in the Sakurai book. So this is exactly the experiment that Bob is doing. So, but important here point is that Alice prepares the state randomly and Bob is measuring also randomly. Measuring randomly means that either he is choosing Z randomly or X. And then Alice publicly declares their basis. So let's do the run. So let's do the experiment here theoretically. So suppose Alice prepares plus x. Immediately Alice writes that the bit is 0. Alice sends this system to Bob. Bob now choose the basis z. So you see that here plus x and z. So you know the getting plus x in when you measure in z basis is half half. So this is a wrong choice. Now Alice chooses minus z. Alice prepares minus z, and immediately the bit is 1. Now Bob has chosen z basis. That means the same as Alice. And of course, if you choose the identical basis, then with 100% probability, always the minus z clicks at Bob's side. Now Alice chooses plus z, Bob has chosen z, and so the same. And then finally, Alice chooses minus z, and Bob chooses x. So now Alice said that publicly declares these are the 4 runs that I have done. So Alice declares not the exact state, but the basis. That means Alice tells publicly in a newspaper or over phone call, which can be tapped by the eavesdropper, that the first run it was X, second run it was Z, third run it is Z, fourth run it is Z. Alice, I want to again stress that Alice does not declare the exact state. So you see, the first one, no match. Second one matched. Third one matched. That means the basis matches. Both Alice and Bob's choice matches. And the fourth one, no match. So what Alice can now tell Bob, or Bob rather, understand that his basis choice doesn't was not same as Alice's, and so Bob said that please discard first and fourth round. And once they discard this, so they finally share the perfect keys. As you see, that since Bob has chosen the same basis as Alice, according to quantum mechanics, the 100% probability minus z clicked at Bob's side, and here plus z clicked at Bob's side, and so the beat will be 1 and 0, as this is the case for Alice. So you see that by this method, Alice and Bob can share perfect keys when without meeting anywhere. So they haven't met, but they just can share the perfect keys. And this is, I have shown only the 4 runs. You can understand that I have to send a sentence or a big plain text. Then these runs has to be done by several times to generate the keys. And then they will use the same as the one-time pad that I have discussed to send the message from one place to another. Now, this is the BB84 protocol. Now, in 1991, Arthur Eckert actually replaced this protocol by using a singlet state. So, suppose Alice and Bob share several copies of the singlet state, and now Alice performs randomly measures in the plus Z basis or X basis. Similarly, Bob measures in the Z basis and X basis. Since the state is entangled and it is anti-correlated, so if Bob gets plus Z, surely Alice will get minus Z. And if Alice gets minus Z, Bob will get plus Z. Similarly, if Alice gets plus X, Bob will get minus X, and so on. So accordingly, Alice writes the bit. So if suppose Alice gets plus Z, Alice will write 0. And if Bob get minus Z, instead of writing 1, in this case, since this is anti-correlated, so Bob writes also 0. Because it swaps, if he gets 1, then he understands actually Alice's part, the measured state is plus Z, and so immediately it will be swapped. Again, the basis reconciliation can be happen that they match the basis. They will only keep those bits when their basis match. This is not, I mean, here a small thing, I mean, kind of disclaimer. Actually, Eckert has not exactly proposed that protocol, but Eckert has shown that first they will do some violation of Bell inequality test, and then they will do the this kind of protocol. But since I haven't discussed about Bell inequality, etc., I haven't gone to that. But this is the same protocol as I have discussed. So the more or less the idea is same. So as I said, they declare their basis publicly, and they only keep those bits when their basis matches, as I discussed elaborately for BB84 protocol. Now, this protocol has been experimentally demonstrated for last 20 years. It's very advanced, this quantum key distribution protocol, and so on. Sorry for the spelling. Now, for example, in 2001, already there are 67-kilometer key distribution protocol was done under Lake Geneva by Nicolas Gisa group. So this is the Nicolas Gisa and his team. They have done several experiments on quantum key distribution. And probably one of the interesting key distribution protocol that was done recently, which is during Football World Cup at South Africa, where it is known as Quantum Stadium Project. And they actually use quantum mechanical method to distribute ultra secure encryption key between two stadiums. One is Durban's Moses Mabhida, and the offsite some joint operation system center. So in this way, they actually can use the quantum key distribution protocol to secure certain to generate keys and to actually do the to use this QKD system for sending messages. Now there are also very nice recent experiments. So these are all done by using photons and polarization degrees of freedom that I have discussed during the experiments in teleportation and dense coding. For example, by Anton Zeilinger's group, where they use polarization degrees of freedom. Here also they have used polarization degrees of freedom or time bin entangled states to do the QKD protocol. On the other hand, in recent time, people understand that there can be some secure key distribution also required when we do kind of computation. And what I discussed last day, that there can be link to be established, which can be some secure and so on. So they have done a experimental quantum key distribution protocol when in a trap turn system. And as it is written, they have used 88 SR plus science, and this was confined in a vacuum chamber. And these ions are separated by 2 meters. And so they have implemented the Eckart protocol. So there are two Alice and Bob shared and entangled states, several entangled states. And then they have done Eckart protocol. They use actually the Bell's theorem, as I discussed briefly, and they establish entangled state and they certify entangled state by using Bell violation, Bell inequality, as I have also discussed during the Nobel Prize in Physics, by which was recognized for certifying entangled state by Bell inequality violation in 2022. And so this exactly that thing they have used, but in trap trans system. And so this is a massive particle, and so they can only separate by 2 meters. Although, as I have discussed also yesterday, that they can now make even a massive particle some 100 meters away. So up to now, I have discussed the QKD protocol, but I haven't talked about the eavesdropper, how this can be secure. So let's, in next 10-15 minutes, I will discuss about that. So this way, how I discuss the Eckart protocol or the BB84 protocol, in this way, you can share perfect keys even when Alice and Bob situated in two distant locations. They can share perfect key provided there is no eavesdropper. Now, in quantum mechanics, eavesdropper can be detected, and how? Now, there are very important theorem that comes into the play. It was also in 1982 when it was discovered that non-orthogonal states cannot be copied. In other words, in quantum mechanics, there are orthogonal states as well as non-orthogonal states. We know that non-orthogonal states coming into the picture because it's because of superposition principle. And so it says that we cannot make a Xerox machine in a quantum world. And here I just want to show that how this works. So as it is in the Xerox machine, suppose I want to clone this die states. So in a Xerox machine, when I want to copy, say, my mark sheet, for example, so I keep this mark sheet. So this is my original state. Then I give a blank copy because this is the A4 sheet I give, and there is a Xerox machine. And finally, I get two copies of I get the original copy and the copy of the mark sheet, and the machine probably gets a bit changed because machine can heat up if you say, for example, if you do a lot of Xerox. So this is typically the thing that we do in our Xerox machine in a classical one. And now I assume that I have that kind of Xerox machine in a quantum world. Now, quantum world, we know from quantum postulates, the only operation that is allowed, only evolution operator that is allowed is unitary. So if non-orthogonal states can be copied, I should be able to find a unitary operator which actually do this task. That means I give the original state, I will give you the blank state and the machine. Then I will get back the original state as it is and the copy of the state, and the machine get changed. And this operation should be we should be able to do in a quantum world when psi and by phi are non-orthogonal. That means the inner product is non-vanishing. Now you can actually prove that this cannot be possible. You just make this part, you actually make it the bra notation, and so you see I have sandwiched these equations with that. And with a simple algebra you find that u dagger u is identity operator, blank and blank is same, so the inner product will be 1, machine and machine is same, so it will be inner product 1. And so we left hand side remain phi psi. Similarly the right hand side remain phi psi square. So if you take phi psi common, then you will get that this equation. So this will be the final equation. And so that means either phi psi should be 0, that means psi and phi are orthogonal, or phi psi equal to 1. And when phi psi inner product is 1, that means psi and phi are the same state up to some factor which is a phase factor. So we assume that there exists a unitary operator, there exists a Xerox machine which can copy non-orthogonal states, and we found that this does not exist. If the Xerox machine has to exist, then either psi-phi are same state or psi-phi will be orthogonal. So it's clearly tell us that such Xerox machine cannot be built in a quantum world. So the non-orthogonal states cannot be copied. And this has an important consequence in cryptographic protocol, as you can already guess, because in quantum world, the in BB84 protocol and in the Eckert protocol, we choose 4 states where you remember that we choose either Z basis or the X basis. And we know from our quantum mechanics class that the Pauli operator, these they don't commute, and that means their states are non-orthogonal, because the sigma z eigenvectors can be up or down. On the other hand, sigma x eigenvector is up plus down or up minus down, so they are non-orthogonal. So if the third party, what we want that the third party Alice sending the state to Bob randomly to one of the state, that either X or Z. If you uh, remember our protocol that we have shown, so here either Z or X. Now these two states are non-orthogonal. So if Eve is sitting here and want to copy via Xerox machine that what state Alice is sending, it's not possible because of this no cloning theorem. So immediately we understand there's like a classical Xerox machine where if you are sending, say, some numbers, then of course the Bob eavesdropper can copy because classically Xerox machine exists. But in a quantum world, Xerox machine doesn't exist, and that immediately gives basic security to the BB84 and the Eckert protocol that I have discussed. Now, this is the no cloning theorem. Actually, the original protocol was the title was a single quantum cannot be cloned. This actually tells us the arbitrary quantum state cannot be cloned. The non-orthogonal version that I have shown was proven later by UN and others. And this was actually proven by Wouters, William Wouters, and Wojtek Zurek. And here I should mention a nice story that Giancarlo Girardi actually have also proven this no cloning theorem. Actually he has given the proof while while referring a article in a journal, and and the journal, that article actually was proven the opposite. So the article was about the cloning is possible in a quantum world. Now Girardi was the referee, and so Girardi actually give a proof in his report that this is no cloning, or the this quantum states, arbitrary quantum states or non-orthogonal states cannot be cloned in his referee report, and send it to the journal and reject that paper. But he has not published that paper. But later on, after some 1 year or 2 years, when Wojtek, Zurek, and Uters published this paper showing that quantum state cannot be cloned. So I was in one of the conference where I was kind of fortunate enough to present, where Girardi was showing this, that he has proven, he has this research article. If you go to Wikipedia now, you can actually find out the referee report and so on, because it is now published. And so I was in a conference where he was showing, and of course William Utters and Wojtek was also present, and he was showing that he has given the proof, and it is known to the community and also now recognized to the community. And this is because this theorem is extremely important in quantum information science, and this has many consequences in building quantum devices. And most important is the quantum cryptography. And quantum cryptography is extremely important, as I said, in any cryptographic protocol is extremely important, from national security to our personal life. And so this since the no cloning theorem is one of the backbone of the entire cryptography, quantum cryptography protocol, so this is highly important theorem. So, as I said, non-orthogonal states cannot be copied without disturbing it, but there are approximately one can clone. This is possible. And so, eavesdropper can clone the state approximately. So, the security analysis, which I am not going today in the discussion, because I think you can already get the flavor that how to do the how quantum cryptography devices can be built. Now, the security analysis is a very involved subject, and it was still developing. And of course, as I said, the backbone is the no cloning theorem. But now the security analysis actually tells us that suppose eavesdropper can clone the state approximately. Now, how much the information eavesdropper can gain, where we have to discard the entire protocol, or we can still continue the protocol. So the security analysis can tells us that threshold that we will allow eavesdropper to get the information. So suppose eavesdropper can get 20% information. Should we allow the protocol to go on? If eavesdropper gets 50% of the information, then we should discard the protocol and start freshly. So these things will be actually is the main research area in when people do security analysis in quantum key distribution. This is also quite advanced subjects. There are a lot of work going on. Steep. There are several open questions, and it's very mathematically involved, and it's very hard now sometimes to address this problem. So, for example, recently we have saw certain security analysis or some certain secure key distribution protocol when there are, instead of Alice sending only the keys, Bob is also doing certain things. So these are the two-way protocols. So there are many variation of cryptography protocol were discovered over last 30 years, and so, and the security analysis people have done, some are solved partially, some are solved completely. So which actually tells us that uh, you have to know where to stop or when to stop. That means you have to know that how much information that you will allow eavesdropper to gain, and you continue the protocol. On the other hand, if eavesdropper get that much of, say, 50% of the information, then you have to stop. So as it is commonly told in our daily life, that we should know where to stop and when to stop. So I also stop here. So thank you very much for your attention and hearing me for 3 lectures.
It's the other way around. I should tell that we should thank you for sparing so much of time, 3 lectures for us, and like in spite of your official as well as home schedule, it's very difficult. I know.
Thank you, Atri.
Okay, Devika, you can go ahead with the question answer session.
Okay, ma'am. So,
Yeah.
thank you, ma'am.